Greetings and welcome to a new video about another control systems topics. We continue with the steady state error examples. In this example, I will look at a different problem, which is a multiple gain control system. We have then two gains, one in the forward path and one in the feedback path, and we would like to then calculate the values of those two gains in order to have a specific steady state error. Of course, we will check our calculation step by step, so we will do that step by step so that you follow that carefully. And we have the simulations in MATLAB to verify our calculations. So let's look at our problem. What we have is the following situation. We have this system given with two systems, G1 and G2, as shown here. Each of them has a gain in cascade, so K1 is the gain in cascade with the G1, and K2 is in the feedback path, which is in cascade with the G2 system. Okay, what we want is the calculation of those two gains if the steady state error is 0.1 for a unit step input. What does it mean? Actually, the following. You apply here a unit step input, and we would like to have a 0.1 as an error. That means if you apply an amplitude of 1, you want 0.9. If you apply, for example, an amplitude of 20, you would like to have 19.9. So it is actually the difference is just 0.1. Now we will see how we can calculate these two values, and we will see also how we can do that in a different way, and there are some sets. So let's move on to the solutions. Okay, in order to do the steady state error analysis, the first step is mandatory the stability check, and for that I will use the Routh-Hurwitz method. This method is already described or given in detailed form using several examples in other playlists, so you can search in this channel for Routh-Hurwitz method or Routh-Hurwitz stability criterion. You will see many examples dealing with this situation. So we need to check the stability first for our steady state analysis. So the first step is the closed loop transfer function, and we will use for that the Mason's rule or Mason's gain rule. What it means is actually the following. The total, I call this the closed loop transfer function, is the forward path divided by the 1 plus the loop gain, which is actually shown here. So this is the forward path, K1 times G1, over 1 plus the total, these four systems actually in as a product. Okay, now once we have substitute everything we have for G1 and G2, that's what we have actually here. Now we need to simplify this. It is actually the next step. You can see here, just multiply the numerator and the denominator by s plus 2 times s plus 4 times s plus 6. Now you will get, of course, rid of these two terms, and you will have this one and the rest actually shown here. Okay, what do I need to do with this expression? Now what we're always interested in is the characteristic equation, which is actually the next step, step 2, for Routh-Hurwitz method, and that's actually shown in the denominator. So from this we get the characteristic equation. So that means this equated equal to 0 is the characteristic equation. Now in order to work out the stability using this Routh-Hurwitz method, you need a polynomial here, so you need to work out this parentheses and have actually a third order system here. So s cubed plus 12s squared plus 44s, and then plus a constant, which is then 48 plus 50 times the product of these two gains, K1 and K2. That is equal to 0. That is our polynomial. So in our next analysis, we will then use this characteristic equation. Okay, now for step 3 in our stability check is generate the Routh table. The Routh table is actually shown and not shown yet, but this is just a polynomial in general form. We have a third order system, so I already given here the general expression for the third order polynomial. This is what we had, so we can now recognize what A3, A2, A1 and A0 is. So we have 4 terms we need to determine from here. Now A3 is in our case 1. Just look at the coefficient here in front of s cubed. A2 is 12 here in front of this s squared. In a similar form for A1 is 44, and A0 is actually these two, so 48 plus 50 K1 times K2. What do we do with this information? Now we need to have, this is a third order polynomial, by the way, there's the characteristic equation, and these are the coefficients. Now we need to set up this Routh table. This is the route table for our third order system. You can see the A3, A2, A1, and A0. Also others, so B1, etc., and C1, etc. So we need to calculate all of these and also substitute the values we have here. So this first step, actually for this B's, we need to use the following expression. And this is again explained in great detail in those playlists about Ruth Hurwitz's stability criterion. So for B1 we can use this formula, which is actually shown in the determinant with a minus sign in front over this A2. So what you actually do in summary, you take actually these four elements as a matrix, so you take then the determinant of that one, you place a minus sign in front of it, and then divide by the A2. That's actually the value of B1. Now if you now add everything in here, because these are given, and also divide by 12 because that's A2 I mean, then you have actually the following expression. So you just work out the determinant. The determinant is of course A3 times A0 minus A2 times A1. So that's actually also what I have done here. Then you get 40 minus 25 over 6 times, again, the product of these two gains. Now B2 in a similar form, but then you actually look at this A3 and A2, and then these two, which are always 0 in the third order system. Now the result here is 0. You can verify this by yourself using again the similar calculation for B1, and B3 is exact same. And then we have 0 for B2 and B3 also. So only non-zero values here, B1. Now the next one is the C1 up to C3. Again, we make a box here to calculate that. Exact same procedure as actually for B's. But then for C1, you actually look at these four. So A3, B1, A0, B2, and then you divide by that B1. That's actually shown here. Again, I set up actually a matrix, get the determinant of that one, minus sign in front of it, and divide by the term above that one, which is then B1. Now, if I now substitute everything in here, I know already that B1 will be 0, so I haven't substituted that. This is the B2, and B1 is some value, but I have also B1 in the denominator, so if I divide it out, and you will actually get exactly the same result as actually this value A0, which is most of the time also the case for this situation. So C1 is also calculated, and C2 in a similar form, and that will be 0 in C3 also. So you only have actually B1 and C1 in this case as a non-zero expressions. Okay. Now what we do next, now we just have now determined everything. We can now substitute what we have. We have now everything. These are of course from our characteristic equation, and these two we have just calculated using these two analysis. Now for the stability check, that's actually where we are heading. We need to check the first column of this table. So this column needs to be checked. And what is actually by checking? We will now shortly look at that, and then determine the values for K1 and K2 for a stability. So let's move on to the next step. So first, the column is interesting. That's actually the required condition for stability. Now we like to evaluate the values of K1 and K2 for stability. Again, looking from the Ruth table, we require, that is the condition, that the following, for the following conditions, we don't want any sign changes. What do I mean by that? We start with the 1, it is positive. Then the 12 is also positive. So I need to keep this positive, the third one and also the fourth one. That means the following: 40 minus 25 over 6 K1 times K2 must be larger than 0. And 48 plus 50 times K1, K2, this one, is also larger than 0. These two, both of them must be larger than 0, not just one. So if I now work it out, I will get for this K1 times K2, just a product, not just single value, must be smaller than 9.6. That's the conclusion here. But from this analysis, I get actually K1 times K2 must be larger than minus 0.96. So I have actually two conditions in between. So the product, so that means actually following, the closed system is stable if I satisfy this condition. So the K1 times K2, the product of that one, larger than minus 0.96, but smaller than 9.6. So if I have, for example, the product here is, let's say, 2, that's fine. But if I have it, for example, 10 or minus 5, that will be not satisfy this condition. I have an unstable system, so the steady state error calculation will not be valid or not possible. So we know now our, let's say, the first boundary condition for our steady state analysis. Okay, let's move on and now check the steady state error actual for this situation. Now, first we need to rewrite this or redraw this diagram, because for the steady state error analysis we want to have a unity gain feedback system, which is not the case here. So I just first merge these two systems and also these two systems. You can see that here. So what might make one block, and then add here actually -1, and then I add another unity gain feedback here, such that we have that unity gain feedback. That's already also discussed in previous videos about steady state error, when we go from a non-unity gain feedback to a unity gain feedback. That's actually the step from this to that. You add a minus sign here in the block, and you have a plus here, 1. So you actually have the exact same as before, but this will of course give you now the unity gain feedback. Now what you then do in the next step is, in this box dotted here in green, you call that just an expression for the transfer function. I just call it PS, and that is the transfer function we need to evaluate the steady state error. So it's not that you do the loop gain, it is actually this loop gain or the transfer function we require. So the PS is again calculated using the Mason's gain rule. So this is exact same. So forward path over 1 plus the loop gain, that's actually K1 times G1 times these two terms. So we need to actually use a parenthesis here. If I now also substitute everything I have here, and then you can see what I have. If I now also work out this, because this can be of course taken together as a one fraction, that's actually the only step I make here. Now the next step is again multiply this, the numerator and denominator, by s plus 2 times s plus 4 times s plus 6. The result is here. You can see again this 1 is then multiplied by these 3 terms. This you will lose actually here the s plus 2 and s plus 4 terms, so you will actually have this, and this is here 5k1 times actually this one completely. Now this is our expression for the PS, which is then required for our steady state error calculation. Now for the unit step reference input, we know that the position error constant, because we are talking about unit step, that is the position error command. The position error constant is the limit of that loop gain, considering of course unity gain feedback, where s is approaching 0. Now we know that L now is also equal to PS, so we can also use the PS, and that's actually shown here. So I've just added or substituted here for the PS in this limit expression. If I now evaluate this at s is equal to 0, so I just substitute for s is equal to 0, so you actually delete all the s's here. So what you get is 5k1 times 6, so it is then 30k1. You get here 2 times 4 times 6 will be 48. You will get here 5k1 times 10k2 minus, this is 0 of course, and minus 6, which is actually the result. Okay, then we have now an expression for kp. Why is it important? Because the error, the position error, is related to that kp, position error constant. So 1 over 1 plus kp. This is, by the way, valid for the unit step input. If you have, for example, not unit step, but the step input has some value, let's say 6, then I have to do that 6 over 1 plus kp, so 6 times this. This is actually straightforward analysis. If I now rewrite this expression for the AEP, for our error, in terms of kp is the rest, so we have the kp is 1 over the error minus 1. Why do I do that? I know EP, which is 0.1, so I have then, this is then 9. So this expression here is 9. So taken together, I have actually the following: 30k1 over this is 9. That is then another expression we need to use to calculate the values of k1 and k2. Okay, let's move on. We have now this, and then we can rewrite this in this form so that we can calculate it more easily. So just 30k1 over 9, and you have this one. Now if you now work out the parentheses here, you will get down 50 times k1 times k2, and then minus 30k1. I can replace this 13 over 9 k1 to the left hand side, make this 0, just an expression which will work out nicely, and you will have this expression. So 48 plus 50 times k1 k2 minus 100 over 3 k1 is 0. So I need to satisfy this expression in order to have a steady state error of 0.1 for a unit step input. That's actually the condition. So we have now following boundary conditions. First, for the stability, we determined this. So the stability criterion says I need this in order to have the steady state analysis. So this is actually mandatory. And then for my condition in this problem, for steady state error, I have this expression. So we have now two boundary conditions. You can, of course, calculate this and make, let's say, an area of solutions using K1 and K2, because these are, of course, related here. But what you also can do, you can, of course, check for possible solutions, because we would like to calculate just the K1 and K2, which will give me 0.1 as an error for unit step input. So we might also say, okay, let's check just a set. So let's say set 1. I just pick up some very straightforward value for K1, just 1. And then look actually to this expression what we have. So just start with the steady state expression, K1. Let's see what we get. Okay, just 1 here and 1 there. So you will actually get this. If I now work this out, you will get for K2 minus 22 over 75. So I have now one set, which is then says K1 is 1 and K2 is minus 22 over 75. So this might do the job. So of course I need to check the stability, so I will do that later. But let's also check another set, because I can also say let's make then K2 1, because that is easier maybe in practical sense, because you need to of course make this maybe in a practical form also. If I make K2 here 1, then K1 and K1 here is still in place, so then I will get this. So again, and I can now again simplify this and calculate K1, which is I think very straightforward. So I leave the details out. K1 is then equal to minus 2.88. So again, another set. So we have now two sets. Maybe you might say, okay, I would like to have another set and would like to reduce the value of K2. So let's say 0.5, because that is more practical. Then you have again this expression here. So you actually put here 0.5 only. So this will be 25. And the rest is exactly the same. You get then K1 is then 5.76. Another set. Of course, we need to check this in the stability condition also. So set 4, the final one. Again, another value, maybe a little bit larger for K1. And then you will have this expression. So K1 is now 2, that will mean 200 over 3, and this will be then 100 K2. Now again, straightforward calculation for K2 will be then 14 over 75. So I have now given you the exact values for these two sets. What we have now is actually the condition for the stability. So we need to check that also. So let's also do that. So set 1 up to set 4. So we have now the K1 and K2 values. We have now determined here. So I have just summarized it in this table. We need to also check the product of that one, because the product of this must be larger than this value, minus 0.96, but smaller than 9.6. So do I satisfy this condition for each set? Let's see for set 1. This times that, of course. So K1 times K2, again, same, minus 22 over 75. So if you do that, minus 22 over 75, that will give you almost 0.293, which is larger than that one. So I do satisfy the condition for stability for set 1. Now for set 2, I have minus 22.88 times 1, which is minus 2.88, which is smaller actually than this value. And I don't satisfy this. So this is definitely not the situation. So this is not a valid set, let's say. It does satisfy the steady state equation, but not the stability. So stability is mandatory, so we cannot use this. We will see that later in the simulations that this is indeed not a valid solution. Now for set 3, I can say, okay, 5.76 was actually for K1 and K2 was 0.5. Take it together, you get 2.88. So interesting is that this is just Einstein inverse of that one. So this will do the job, because 2.88 is smaller than 9.6, so that's fine. Another one is 2 times 14 over 75. So you will get 28 over 75. So 28 over 75 is actually close to 0.75 373, a little bit larger, and that is again larger than that one but smaller than that one. So again, set 1, set 3 and 4 do satisfy the conditions here for our boundary. So we can then say we have some sets, we can then select actually which one performs better in terms of maybe other parameters. So let's then also look at the simulation results. So first start with a close-up response to unit step reference input, but then for set 1. That's actually again the K1 and K2 for this value. So this is then the approximate value for that exact value I have given. You can see this is the system, and I have also given again the final value, but also some other values. You can see here the settling time and rise time, and the overshoot is here 0 because there's no overshoot. So that is maybe interesting for some applications. Rise time is 2.21 seconds, and the settling time is almost 4 seconds, so 4.04. So final value is 0.9. So for unit step input, I get 0.9 as an output. So the error is 1 minus the final value is 0.1, which we wanted. So that is then good. And this is a stable system because it actually settles down to a final value. It doesn't explode to some infinite value. Okay, this then confirms our simulation for the first set. Let's also look at the second set, set 2. We said it was unstable. You can see already that what's happening is 10 to the power 25 and going all the way to that value of 9 times, etc. in 40 seconds for this set. So this is definitely, for this system, you can see this is definitely unstable. And I cannot use this because I said in my discussion that the stability is mandatory to able to do the steady state error calculations. The steady state error formula gave us these two values, so that was actually valid according to that formula, but stability check is actually showing us that this is not a valid solution. So this is mandatory. So this is also again a confirmation that this is not a valid set. Okay, let's look at the set 3. Set 3, this is the response for that, using 0.5 for K2 and then 5.76. This is again the system we had, and this is again a final value of 0.9, again 0.1 as an error for unit step input. These are the values here as a summary in the table. You can see the overshoot is quite large, 47.3 is interesting. The rise time is much smaller, so it's actually speeding up. The setting time is also speeding up, 3.09, and again final value and also the steady state error according to the specifications. These were of course not the specifications. We are not interested in that in this specific problem about steady state error, but it is interesting that we can also select the best of these solutions. So let's also check that shortly. The final one is and again this is stable system. Now let's also check the final set 4. These are the K1 is 2 and K2 is 14 over 75. That was actually the condition. This is again the system, and again our final value of 0.9, which is then what we required. And again here the summary, you can see it's almost 1.8 or 1.79% for the overshoot, very small. You can see the rise time is 0.773 and the setting time is 1.17 seconds. And again the final value and also the error from that. So it's a quite nice response. So, and again this is a stable system. So we can maybe decide that this is maybe the best solution from these sets. So let's then also check the summary for all sets. Of course, set for T2, which is then actually the second set, will not be here because that is not a stable system. So T1, T3 and T4 designate actually the responses close to transfer function responses for unit step reference input for each set, for each gain set. Now what you see is all of them approach 0.9, and the orange has the largest overshoot. The blue one has not an overshoot, but it's actually also the sluggish, so actually also very slow. So the yellow one is sort of the compromise between those two and maybe the best solution. So let's maybe also check that in great detail in the parameters. So T1, T2, you know that this is unstable, but T3 has a very high overshoot, and T4, which is 1.98 actually, and this is 0 of course, so I can say, okay, I don't want any overshoot, then you can go for T1, but this set is much better. You can see that rise time is also much smaller, and also the setting time is almost 3 times smaller, maybe close to 4 times. And this is then the same, so for the steady state error. And the output is just 1.8. So if you can handle this, accept this, you can say, okay, this is a good solution. And maybe the best solution in this case for our set. Of course, you can move on and generate a number of other solutions for also on other sets for gain. So this is not just absolute sense the only solution we have, but you can see that this set, in this case, probably gives the best result, considering also other specifications like overshoot, rise time, and also the settling time. All right, this is for our example about the steady state analysis and steady state error about a system having 2 gains, so multiple gain. If you have any questions about this example, please let me know and I will try to answer them as soon as possible. Of course, don't forget to share and like this video so that we can reach more people for this very interesting topic. See you next time in another interesting video. Stay tuned and take care.